As we saw on the previous page, that a function doesn't have to have an absolute max or an absolute min. You're not guaranteed that. But now we state conditions that guarantee the existence of both of the absolute max and the absolute min. And that's given by what's called the extreme value theorem. So stated here, a continuous function will always obtain a maximum and a minimum on a closed interval. So here we're talking about absolute max and an absolute min. So what are the conditions that guarantee the absolute max and absolute min? First of all, the function has to be continuous. Second of all, the function has to be defined on a closed interval. Those two things guarantee the existence of an absolute max and an absolute min. So let's take a look at the three figures on the previous page and see why, whether this extreme value theorem applies or not. In the first figure, the function is clearly continuous, no breaks, no jumps, no gaps on the interval from 1 to 5. The interval is closed. Notice it includes the endpoints for it to be closed. So the extreme value theorem applies and we get the maximums that were stated in the example. You can see there's no breaks or holes in the graph. It's defined on a closed interval going from 1 to 5. So we have an absolute max being 4 and an absolute min being 1. On the second figure, the problem here was that the function is clearly continuous on the interval. However, the interval is an open interval. It doesn't include the endpoints. It's got to include both endpoints for it to be considered a closed interval. So the extreme value theorem doesn't apply here. So we're not guaranteed. You could have an absolute max and an absolute min. You might have one or the other, but you're not guaranteed to having either. In the third example here, again, this time the interval is closed, but you can see that the function has a break at 3, so it's not continuous at 3. In fact, it shoots off as x is approaching 3 from the left, it goes to positive infinity. As x is approaching 3 from the right, it goes to negative infinity. So this function, even though it's defined on a closed interval, does not obtain a max or a min. But furthermore, the important part is the absolute extreme principle. The extreme value theorem does not apply to either one of these two functions. It does apply to that one. That's why we have an absolute max and an absolute min. Okay, so let's go back to now. The extreme value theorem kind of states that these conditions being continuous and on a closed interval are sufficient. However, they're not necessary for having an absolute extrema. Take, for example, the graph of cosine x, which is right here. Here's a graph of cosine. You can see that cosine obtains a largest value of 1 and a smallest value of -1 over the entire real line, which is not a closed interval, right? So here I'm talking about the interval then would go from negative infinity to infinity. This is an example of an open interval. So m can be any number you want it to be, where it has a maximum value of 1. So for example, we can take this to be m right here. See there, it reaches a maximum output of 1. You can take m to be any even multiple of pi. So it can be at 2 pi, it can be at 4 pi, it can be at 0, -2 pi, -4 pi, and so forth. However, where does it obtain its minimum of -1? You have your choice for any one of these, the x coordinates of these valley points as your m. So I chose this one to be m. You could have chose it to be pi, whichever one you want to use. So the absolute minimum occurs at infinitely many x coordinates, and the absolute max occurs at infinitely many x coordinates as well. So let's just say that we have these conditions, that the function's continuous and it's defined on a closed interval. Where do we look to find the absolute extrema? Well, that's what's called the absolute extrema principle. This is what's called the closed interval form. So where do these absolute extrema occur that are guaranteed by the extreme value theorem of a continuous function defined on a closed interval? Well, they can only occur at two different locations. They either occur at the endpoint of the closed interval, these are what are called endpoint extrema, or they're going to occur at a peak or valley point, which are called the local extrema. Local max, local min. Okay, so for example here I have a function that is defined. I got to make sure that we show that it's really a closed interval here. And notice that m is occurring here at this so-called peak point. I'm sorry, the absolute max is occurring at this peak point, so m is going to be the x coordinate of that point right there. Notice that bring that up a little bit. Notice that little m is the x coordinate of the right endpoint there. So in the figure, the absolute max occurs at the local max, the peak point, and the absolute min occurs at the right endpoint. So you see, it's either going to be one of these two. In the next example I have here, notice that the interval goes from a to b, and both the absolute max and the absolute min occur at the local extrema. This is the valley point right here. Or what's called the local minimum. And right here is the peak point. So you see that the x coordinate of that peak point is going to be capital M. The x coordinate of the valley point is going to be little m. So that's the only places they can occur, at the endpoints of the interval or at the peak and valleys. If it has more than one peak and valley, you got to take the highest one. Okay, so let's go on to some quick and obvious observations. The first corollary says that if a function is increasing on a closed interval, here it is, I got the function going from rising to the right, going from left to right. So you can see that if the interval, the function's increasing over the entire interval AB, then the absolute minimum occurs at the left end point, which is x equal a. So this is the left end point A. You see how, look, there it is here. So this is your A, and then the absolute max occurs at the right end point, so that means that capital M is B. So for an increasing function, the absolute max occurs at the right end point, the absolute min occurs at the left end point. Now flip the picture around. Let's just say that the function here is decreasing on an interval. Now it switches around. This time the absolute max occurs at the left end point and the absolute min occurs at the right end point. So one other thing we need to point out, though, is the following. The absolute max and the absolute min are what we call closed interval dependent. In other words, you change the closed interval that the continuous function is defined on, it more than likely is going to change the absolute extrema. So here's an example of a function that I have here. We'll just say this is a graph of y equal f of x. If I take the interval to go from 1 to 5 as my closed interval from here to here, you can see that the absolute max, so this is going to be your m is going to be 3, and the absolute max is going to be, when I plug 3 into the function, I get 4. That's the y coordinate of that point right there. So 4 is the absolute max occurring at x equals 3. The absolute min is at this valley point down here. So again, look on the interval. So I'm only looking for the absolute max and mins at either the endpoints or at the peaks and valleys. So it's at the peak is where the absolute max occurs of 4 at x equals 3. The absolute min of 1 occurs at x equals 2. Now let's make the interval, the closed interval, larger. Let's go from 0 out to 6. So now we're going from here to here. Again, I check on the endpoints and the peaks and valleys. So again, I'm still with the same absolute max and the absolute min occurring at the same locations. However, if I make the interval smaller and go from 4 to 6, now let's see here. Let me use my ruler and put it right here at 4. Here's the graph is going to start here and it's going to end right there, where you can see that the absolute max is going to occur at the left end point. So capital M is going to be 4, with the absolute max being, when you go back across, it looks like it's 3. So that's the absolute max of 3 occurring at 4. And M, I can take it to be any one of these numbers between 5 and 6 inclusively, and the absolute max will be 2. And I just took little m to be 5. I could take little m to be 5.1. I can take little m to be 6. Doesn't matter. But notice that the absolute extrema, these numbers have changed from those over there. And one final note, that I really don't even need the absolute, I don't even need the extreme value theorem here, because if I take the interval to go from negative infinity to infinity, which is not a closed interval, f still has an absolute max and an absolute min. The extreme value theorem doesn't apply there. But and all that means is that the extreme value theorem is giving you conditions that are sufficient to guarantee absolute extrema. If the extreme value theorem doesn't apply, all that means is that you're not guaranteed an absolute max or min. The function may or may not have it. Now let's see the connection between circumscribing rectangles and the absolute extrema. In this case, the absolute max. Now it says to circumscribe a rectangle over the graph on a closed interval. So we're going from, here's my closed interval, from here to here. Then I use the absolute max output of the function on the interval. Remember, since it's a closed interval and the function's continuous, it's going to have an absolute max that's going to occur either at an endpoint or at a peak point by the extreme value theorem. By the what am I calling this? The absolute extrema principle. So it's occurring here at the peak. There's the peak right there. So I draw my triangle, and now I see when I draw my rectangle, you can see that it is over the entire curve. The entire curve is inside the rectangle. That's what I mean by circumscribing the rectangle, making it over the curve itself. Now, if we want to inscribe a rectangle, instead of us using like over here where we use the maximum output, now I'm going to use the minimum output. So this time the absolute minimum is occurring at the right endpoint, so that's little m right there. So come up here, square it off that way, and now there's my rectangle right here like this. So now you can see that the entire rectangle is inside, it's inscribed the graph of the function. Notice the gap that's here. Up here, notice the gap that's in between, that's above the curve but below the rectangle. Okay, so let's go to so what happens if I pick a number, an x-coordinate c, that is not equal to little m or capital M? In other words, where let's say at a point that's not going to lead to an absolute max or an absolute min, to an absolute extrema, then you see that if I were to pick a number c at random in the closed interval, I come up to the graph. This is my curve y equal f of x, of course, and I square it off there. Then I get the following looking rectangle. Notice that some of the curve is above or outside the rectangle, and some of the rectangle is outside or above the curve. See, that little piece right there is above the curve. Now remember, capital M is where the absolute max occurs. It's occurring at that peak point, and that's capital M. Little m is where the absolute min occurs, and that's down here. So if I were to use this rectangle, it's all inside the curve. If I use the absolute max, the entire curve is inside the rectangle. Pick any other value c, then some of it's going to be above, some of it's going to be below, and so forth. Now, just want to point something out to you. Do you see that if I were to evaluate the function at capital M, at c, and at little m, then this has to be true? Why does that inequality have to be true? Well, because f of little m, that's the absolute min. That means that that's the smallest output over the interval. F at capital M is the absolute max, and that's the largest output over the interval. So that means that f of c has to be intermediate in between those. Just pointing that out. We'll see how that's going to play a role later on. Finally, just a kind of summary of the notation, just to remind you, when I'm throwing all these different symbols around, little m is the x-coordinate where the absolute minimum occurs for the function f. Capital M is the x-coordinate where the absolute maximum occurs. If I want to find out what the absolute min is, I take m, plug it into the function, and f of m is the absolute minimum. Look at that right there. That's the absolute minimum right there. F of capital M is the absolute max. That's this right in here. And c is just any number in the interval, or any point in a closed interval from a equal to b. So c can be any number in between, or it can be one of the endpoints. It doesn't really matter. So f of c then, this thing right here, is just the output at some arbitrary number, c. Okay, now, so let's go back to page 2 of the area notes and continue. So here on the top of page 2, it says to take this region R and subdivide it using 6 rectangles. So now I already took the liberty of drawing the 6 rectangles, and it says to use upper sums. So first thing I got to do, I got to figure out how to divide the rectangles, and I want to divide them up in such a way, even though it's not drawn to scale, where all of them have the same width. It just makes the computation a lot simpler for me, or for us, I should say. Let's go back to page 1. With 3 rectangles, it was kind of obvious that just make each one have a width of 1 here. In both of these cases here. Notice I want to point out to you that the upper sum using 3 rectangles ended up being 21. The lower sum using 3 rectangles ended up being 14. So we ended up with this double inequality, that the actual area of the region is between 14 and 21. So you can see that if I use 3 rectangles, I have a width of 1. So if I want to go to 6, probably what I have to do is cut each one of these in half. So it looks like the width of each rectangle is equal to 1/2. So from here to here is a half, and so forth. I'm not going to draw it in. It's kind of small here. So let's take a look at the first one, capital R sub 1. So on this little interval, I have to find the largest output. Well, the absolute max, since I'm using upper sums, is going to occur at the right endpoint, so it's going to be right there. So say that the area of our region here is approximately S of 6. I really should just say that it's going to be less than S of 6. So this thing is going to be summation from I equal 1 to 6 of, using the same notation we used on page 1, capital A sub capital R sub I, which means you take the area of rectangle 1 plus the area of rectangle 2, and you keep adding them up to get to the area of rectangle 6. Length times width, right? So for the first rectangle, the width is a half. And now let's get the height. The height looks like it's going to be 7. Now on the second rectangle, notice, well, let me go back to the first one. Notice that on the first subinterval, notice that the function was increasing. That's why the absolute max occurred at the right endpoint. On the second rectangle here, the function's decreasing, so its maximum occurs at the left endpoint. So again, I'm going to get 7 for the output. It's continuing. On the third rectangle, the function is increasing, so it's going to occur at the right endpoint. So that looks, when I'm just going to estimate it, it looks to be about 5.25. Let's go to the fourth one. On the fourth one, function's increasing here on the fourth one. So it looks like it's going to occur at the right endpoint, and that's going to be 6. Let me put this down here. On the fifth one, the function's increasing, occurs at the right endpoint. Again, I'm going to have to do a little estimation here. Kind of looks like 6.5. Finally, on the sixth rectangle, increasing, occurs at the right endpoint, and that's 8. Now, this right here, you can see how this really simplifies the computation. Since 1/2 is included in all of these, I can just factor out the 1/2. Just add the 7, 5.25, the 6, 6.5, and then the 8. And that turns out to be, let's see, that's 14, 20, 28, 28 plus an 11.75, and I get 39.75. Then divide that by 2, and you get 19.875. So now, notice that this number is less than S of 3, which was 21. But notice again, look at the picture, see the gap here. So that means that what we have right here, that the area of this region is less than S of 6, which was less than S of 3. So more rectangles, notice how the rectangles are getting thinner, then the approximation gets better. So I can do the same thing with the lower sums with 6 and improve on that inequality that I had written on the bottom of page 1, that was that A sub r was between 14 and 21. Now I found that the upper estimate is 19.875 with 6 rectangles. I can get a better number for the lower sums using 6 rectangles. So let's just quickly make some observations here. The lower sum, little s of n, is always less than the area of the region A sub r, and the upper sum, capital S of n, is always greater than A sub r. This can be written as S of n is less than or equal to A sub r, less than S of n, and the upside down A means for every n. As you increase the number of rectangles, the rectangles get thinner. See that? Use more rectangles, and this is what you hope happens, that the approximations get better, as we just saw there. Finally, this is what we would want to happen. As you let the number of rectangles increase without bound, more and more rectangles, and they're getting thinner and thinner and thinner, then the upper sums approach the actual area of the region A sub r. The same thing can be said about the lower sums. So symbolically, if you take the limit of the upper sums as the number of rectangles increase without bound, you should get the area of the region. If you take the limit of the lower sums as it increases without bound, you should also get the area of the region. Doesn't matter which one of these you do. Okay, you can see right here, more rectangles and the approximations get better because the rectangles are getting thinner and thinner. So from here on out, the rest of the handout is just trying to make the computation of S sub n, capital S sub n, or little s sub n to be as easy as possible so that we can perform these limits to get the area of the region. So that's what the rest of the handout is about. And this method Now, just to show you about computationally easy, you see up here, by making one of the simplifying ideas, by making the width of each rectangle the same, then I'm able to factor out this 1/2 and just add the outputs of the function in order to get this 39.75, and then I'm multiplied by the common thickness of each rectangle. They don't have to be all the same width, but it always makes the computations easier if you take them to be the same width. Finally, this process of subdividing with a lot of rectangles, this is what we call the slice and sum approach, or the slice and sum method. You slice it up into a bunch of little rectangles, and then you sum them up. The only problem is, the thinner you slice, the more rectangles you have, the more areas you have to add up. In fact, look what we're going to end up doing. We're going to let the number of rectangles increase without bound. There's no way you're going to be able to do this computation, how should I say, physically. So we have to use some of the previous work on summations and area in order, and limits, in order to figure this out. Okay, we'll continue here in a minute.